Good evening and welcome everybody. This is Obi-Wan Pez for Ensimplex Pachinko. Gonna be doing some math tonight. So, as always, any questions that people have will supersede any plans that I have to do little things. I thought that we would look at a couple of things that Another Roof had done on his YouTube channel. I don't have everything worked out, so it's kind of an opportunity to just explore the space and see what we got. Okay. Sorry, I think my son got up and headed to the bathroom again. Calling him out. Alright, so just looking at these real quick. That is yet another multiple of 3. So we'll highlight that there. That one is not multiple of 3, so it's going to eventually create another branch. Hang on one sec. Alright, anyway. Wild child appears. 6-4. Alright, so another branch is going to occur off that. Alright, these up here we've got 213 is a multiple of 3 itself, so again it's not going to oscillate to create anything else, which does mean that all the rest of this stuff is kind of unnecessary to write out, because it's just going to be powers of 2 multiplied on 2. Seriously. Right, powers of 2 multiplied on a 213 forever. I was trying to figure out if there was any sort of pattern in terms of, like, you know, is there a way to figure out when we're going to branch off and get a power of 3, but, like, not seeing anything. It's not yet. Right, and these are all mutually primed at 2, since they are just multiples of 3. Six, 3, 2, okay. And, right, this stuff isn't because it's already got branches coming off of it. Let's see if we can figure this out just in this moment. So, the numbers that we see branches coming from are going to be, I mean, I guess we could include 4 here, but, like, kind of breaks the whole point here. So we got 10, we got 40. We've got 52. We've got 34. 22. 28. 88. Right, now there are going to be some things that we definitely have, they're going to be, say they've got to be 4 mod 6, I think. Something else we looked at last time. 46. Yeah. That's 4 mod 6. 160. $162 is divisible by 6. Yeah. Okay. So we know that all that stuff is going to be 4 mod 6. And then so these are equivalent to 4 mod 6. Alright, 16. And all these also belong over here. No, we already got 10. Alright, 64 is another one. So what's the further subset of these things? Okay, they've all got 2 digits that add up to 10. Doesn't necessarily help or mean anything, but you know, with the exception of 10. Wait. That's an interesting one. So they don't all have like 4s or don't all have 2s or 6s. A few of these look like they have 4s and 6s, but like that's it's like either or. 10 is the sum of 4 and 6, but other than that, I don't know. Just starting to think numerology over here. Pi reference, anyone? All right. That'll be good enough for now, anyway. So the question that I wanted to pose was on another roof. On YouTube, please go check out their channel. Good content creator, has done several several videos on MAFS, which is the like mathematical analysis in film something or other system, which I thought was kind of funny and hilarious, given especially that he does have that particular accent, where TH becomes F. So so the reason for me bringing up Pi specifically was the movie Pi was in one of his videos. I think it was the Witch one that we're planning on talking about a little bit here. Which of course was done on Halloween, which of course means that like this is way out of season, but hey, whatever. So he went out to Oxford to go meet with Dr. Tom. Of course, I'm going to forget his name now. Hooray! Crawford. Just remembered. So he went out to Oxford to go meet with Dr. Tom Crawford, who he was like, I just went to the University of Manchester or whatever it was, so like, you know, had no chance of getting into Oxford. But I thought I'd sit down with, oh no, he applied, but he was not given an interview, and so he was asking Tom Crawford if you wouldn't mind, would you like sit and interview with me? And he was like, yeah, sure. Just to have some fun. So the problem that they gave at the beginning of the video, and I haven't looked at the solution, but I've got like a page worth of scribbling and not much to show for it. But of course, that is mostly that is mostly the kind of like direction that they would be more interested in for like all of these interviews. And this is also a tip for anybody who needs to do interviews in the future. Like, if you're going for a professorship, they're probably going to ask you some highly technical questions and look for you to like explain some stuff. And if you're going into a teaching position, they're going to want you to be able to like explain anything you need to explain on the spot. So let's just, you know, test your algebra skills right now. You know, if this person here, who is one of your potential future colleagues, were to come to you as a student and then say the typical things that students say and things like that, you know, how do you react, and how do you approach each of these problems that they give you? Right? That stuff they actually want an answer, and they want it quick, and they want to make sure that you understand that you're not supposed to like give the student the answer, but help them work through any of these particular problems. But in the case of this, I don't know if it was a PhD program or what, but you know, in theory, we could say, yeah, it's a PhD program. Maybe it was just grad school. In a PhD program, like, they would not necessarily be asking you to look for an answer if you don't actually know what the answer is, because it's possible, unless this is something that's supposed to be in your qualification, right? If you are supposed to already have known this, then it's kind of important that you probably know it. But at the same time, if it's like, you know, an area of math, let's say, I never took number theory, for example. Like, that was just never in my program because I was a math education major. And then when I went to grad school, I did mostly differential equations. So, like, I just never ended up taking number theory. So if they ask you a real analysis number theory type question, and you're like, well, I don't know how to do it, you probably want to be straightforward about that. I don't know how to do it, but let's see what would happen if we just play around a bit. All right, so the question is, we have a function, f of x, when added to twice f of 1 over 1 minus x, we get x. Right, so this is an implicit function. It's not going to be super simple, I don't think. And we want to start like probing this thing and figuring out what could we do in order to figure out what is f of 3 is the goal. So just fairly straightforward question, but not necessarily going to be a fairly straightforward answer. So for this particular one, I would say, you know, your first goal or your first question is going to be just what does f of 3 look like when you just plug it in. So if we just literally plug stuff in, right, f of 3 plus 2 times f of 1 over 1 minus 3 equals 3. Okay, this is going to be f of 3. And I think this was his particular approach as well, was just, okay, let's plug the number in and see what happens. This is going to be 1 over negative 2, so negative a half just in total, is equal to 3. Okay, so f of 3 is going to be implicitly defined as 3 minus 2 times f of negative 1 half. All right. Not particularly helpful in terms of, like, I'm sure this has an answer. So, yeah. We're not going to be able to look at this and be like, I get it. We just want to come up with, like, some other way to get more information about this system, or about this individual question, and try to see if there's any way that we can come up with something better than this. So my first instincts are probably different from anybody else. But from here, I was like, okay, we could either go one direction where we just start plugging in numbers. Right, this is a strategy. All right, and then find some sort of pattern. So, like I said, plug in numbers, find some patterns. If that doesn't work, or if it's you know, not particularly working toward what you're trying to find, then my next instinct was, okay, what about calculus? Right, I know how to find derivatives, and I can do derivatives with I can do derivatives of composed functions like this. Not a problem. Can figure out if there's some sort of pattern, there's some sort of like better way of seeing this. Okay, so we take some calculus methods, probably derivatives, and in fact this led me to the realization that this might work as like a differential equation. And since that's my specialty, right? Like, you already know what it looks like implicitly, so try to find it explicitly, if that's even possible. The other option was, with differential equations, we might be able to do a series solution, either to the differential equation, or, that gave me another idea, was do Taylor series. Right, this thing right here, 1 over 1 minus x, looks an awful lot like a Taylor series shortcut that I know. The problem here is that that's on the inside of the function, not on the outside, so might be an issue. Okay. I'm just now realizing we might be able to figure out, like, we might be able to do some weird thing with recursion and say, like, okay, if f of x is equal to, we could shift stuff around, right? So, if f of x is equal to x minus twice f of 1 over 1 minus x, then we might also be able to say, okay, now f of 1 over 1 minus x is going to be equal to, this is probably going to be nasty, 1 over 1 minus x minus 2 times f of 1 over 1 minus 1 over 1 minus x. So recursive fractions like this aren't usually something that I would recommend. But there is an interesting way in which recursive fractions end up like creating something else. It's maybe a little weird, I don't know. We'll see. And, oh. Yes. I think we might be able to do this. Because f at 3, right? F at 3 is going to allow us to plug all this in. Then when we get here, we do the same thing, and we say, what is that going to get us when we plug in this? So then I need to know what is 1 over 1 minus 1 over 1 minus 1 over 1 minus ... off to infinity. All shucks. Doing all right. How are you? Okay, so if this is finite, $26X. I mean, neither, but me personally, I think most of the time I prefer Wendy's. Between those two, yeah. Yeah. Oh, Burger King, man, I say. No, not really either. Given the choice between all three of them and only those three, probably Wendy's. But maybe Burger King. I think probably it depends on my mood. It may also depends on what kind of fries I want. There may be other factors. um, yeah, so typically we go to like... If we have to stop somewhere, right, then most of the time I'm either looking for like Panera, Five Guys we've had every so often, just mostly because it's like, if you want burgers, you go to Five Guys. The one problem with that a lot of people have is that they have open like vats of peanuts. You could just dig in and take some back to your table. So there is peanut oil and peanut dust from the shells just literally everywhere. You cannot escape it. Do not go to Five Guys if you are allergic to peanuts. And I think all their stuff is fried in peanut oil too. So. Alright, so this would collapse if it were finite. So this would be 1 minus 3. It's going to be negative 2, so this is negative a half. 1 plus a half is then going to be... yeah, okay. Maybe I'll go one more, just so I don't have to erase anything here. Right, so that's a negative 1/2. We're going to subtract it, which means we're adding to 1, which gets us 3/2, which flips it over. It's going to make 2/3. Over 1 minus. 1 minus 2/3 is going to end up being 1/3, which flips up and makes it 3 again. Okay, so this has a cycle of 2. So if it ends with 1 over 1 minus 3, this is going to get us a negative 1/2. And if it ends here, that's going to get us a 2/3. Right? And we just go like this, right? Gets us a 3/2, and the denominator flips up and makes us a 2/3. Positive 2/3. Okay. So that's oscillatory between these two things. If it's infinite, then we have a problem, because that's not going to converge. So, I mean, it's possible, I guess, that it could be like we're going to take the average of those things because I hate OB. Maybe 4/6, 3/6. It's going to be 7/6, which gets us a negative 1/6 is the average of those two things. I really hope that's not the answer. That's not the F value anyway, but okay, that's a weird sidetrack that we could think about later. I don't think that's going to get us anywhere. That's just going to get us the value that's being plugged in. We already know, right, the value that's being plugged in literally here. Right, is just going to be negative 1/2. So be negative 1/2 minus 2f of 2/3. Oh. But the next time it cycles around again. Interesting. F of 1 over 1 minus 1 over 1 minus x. Right, when x is equal to 3, this is going to get us f of 2/3 is equal to 2/3 minus twice f of 1/3 layer. So this would be 2/3 here minus 2 f of negative 1/2. Can those exist at the same time? I think I may have contradicted myself somehow. Nope. Oy. That's fun. I clicked the little button on the side of the stylus. Apparently brought up the right-click context menu. Okay, so if we rearrange this, right, this is going to be 2/3 minus f of 2/3 is going to be equal to 2f of negative 1/2, which then you divide by 2, and f of negative 1/2 is equal to 1/3 minus 1/2 of, this is weird, f of 2/3, that's 1/2 of. Sanyolo, how's it going? So this is off of another roof from YouTube, and he did an Oxford interview question with Dr. Tom Crawford, which is this thing here. If we have f of x is equal, f of x plus 2 times f of 1 over 1 minus x is equal to x, then what's the value of f of 3? Right, so what's the value of f of 3? And So like the first thing that I did and the guy from another roof did was let's just plug the number in, see what happens. So we get f of 3 is equal to 3 minus 2 times f of negative 1/2. And so at this point, it's like, well, I don't know how exactly we're going to get anywhere from here. We could plug in a whole bunch of numbers and find some patterns. I said earlier we could do some calculus, create a differential equation from a standard equation and maybe get it into an explicit form. Maybe find a series solution, maybe do Taylor series, and maybe do this nest composition thing where I said, okay, if we've got f of x is equal to x minus 2f of 1 over 1 minus x, then this is going to mean that f of 1 over 1 minus x, we could compose this and make it equal to 1 over 1 minus x minus 2 times f of 1 over 1 minus 1 over 1 minus x. Right, yeah. So we've been kind of bouncing around with this a little bit. It is interesting, like I said, it bounces like all of our internal portions, the thing that we're plugging in, is always either going to be f of negative 1/2 or f of 2/3 if we do this finite extension of all the things that we're finding here. So if we do, f of 1 over 1 minus x, where x is 3, this is going to get us negative 1/2. If we do 1 over 1 minus 1 over 1 minus 3, then the little term there is going to get us a negative 1/2, and then we do 1 minus negative 1/2 is 3/2, and it flips up and becomes 2/3. Yeah. So I said, okay, that means that we're going to get that f of negative 1/2 is going to be equal to negative 1/2 minus 2 times f of 2/3, and also f of 2/3 is going to be equal to 2/3 minus 2 times f of negative 1/2. So if we bring those two facts together, I'm trying to see if we can bring them together and say like, oh, these are actually the same thing, because I think this is now just a 2x2 system of equations. Which is absolutely insane if that's true. So f of negative 1/2 from this perspective got us negative 1/2 minus 2 f of 2/3. So if we subtract, let's subtract the bottom equation from the top one. So that's going to get us a 0 on the left is equal to 1/3 plus 1/2 is 5/6. And 2 minus 1/2 is going to be positive 3/2 f of 2/3. We have a number now. Yep. That's how it works. I like it. So this is one of those weird things where it like comes at you with a problem that looked really hard and has a really simple solution if you can find it. All right, multiply by 2/3 both sides. Oops. So f of 2/3 is going to be equal to negative 10 over 18 or negative 5 over 9. Well, we're going to keep working backwards. So we got it. So that means that if f of 2/3 is going to be negative 5/9, then f of negative 1/2 is equal to whichever one we feel like, negative 1/2 minus 2 times negative 5/9. It's going to be positive 10/9 minus a half. So this is going to be 9/18 from 20/18, right? Yeah. It's going to be 11/18 for f of negative a half. Yeah, no, we're getting there. And then f of 3 is going to be equal to 3 minus 2 f of negative a half, which that is negative 2 times 11/18, 22/18 from 3, which is 54. 54/18 minus 22. I mean, if I did something wrong, definitely tell me, but 32/18, which, yeah, divide by 2 is going to be 16/9. F of 3 is 16/9. Ian Stuggy, good evening. So when we compose the function, right, we go back and if we do this recursive right, so I figured out back here that if we continue doing this over and over and over again, and do a finite recursion like this, then every time we go down, it's going to either repeat as negative 1/2 or positive 2/3. Like, there's no other solution. There's no other different number to get when you do the recursive fraction. So, alright, so let's go back then. Make sure that I didn't mess this all up. So f of x plus 2f of 1 over 1 minus x is equal to x, which means f of x is equal to x minus 2 times f of 1 over 1 minus x. Okay? When x is equal to 3, this is going to be a negative 1/2 inside the parentheses. And that's f of 3 is equal to 3 minus 2 times f of negative 1/2. Now, we knew this from before, right? This is something that I did back here. That we said that this is just one of the equations we need. But if we go forward and nest the 1 over 1 minus x in x, like in place of x for f of x, then what we end up getting is no longer x, but 1 over 1 minus x here, minus 2 times f of 1 over 1 minus 1 over 1 minus x. Right? So then from here, we can then build this out further into further nestings. Which statement? F of 2/3. Oh. So here, right, 1 over 1 minus 2 is going to be negative 1/2. then here we end up getting 1 plus negative a half, which makes, oh my god. Which makes 3 halves. Flip it over, we get 1 minus 2/3, which is 1/3. Oh, flip up. Wait, hang on. You mean this one? The one before it. Because this one's got... Oh, man. Right, so 1 over 1 minus 3. 1 over 1 minus 1 over 1 minus 3. 1 over 1 minus 1 over 1 minus 1 over 1 minus 3. Curses. And then 1 over 1 minus 1 over 1 minus 1 over 1 minus 1 over 1 minus 3. Okay. So here we end up getting negative 2 on the bottom, so it's negative a half. So that means that all of this is just going to be negative a half. So that's going to end up with, right, 1 minus negative a half is going to be 3 halves. Flip, we get 2/3. So all of this is now 2/3. Gotcha. Okay. So 1 minus 2/3 is 1/3. 1 over that is going to be 3. So then that's this stuff, which is 3. Which then makes the same negative 1/2 that we did before. Okay. Thank you. Something weird's going on out there. Okay. So, right. One of these is not correct because it's not immediately going back. It's just making a cycle. Okay. So... Alright, so what do we actually get? Right, f of negative 1/2 is going to be this thing. Cool. No, right? My spouse has been moving stuff out of our house at a very large rate, so... Which is, of course, good if we're moving overseas, but nonetheless. Okay. Right, okay, the 2/3 one. He's going to have 3 as the... Alright, I'm going to rewrite this, and we'll hit this add thing. Be right back. Kill the pre-rolls and all that stuff. Okay. So, rewrote this as a 3x3 system of equations in terms of matrices so that we can get a simplified system and all that good stuff. Sheaf site stack. Good evening. Substituting 1 minus 1 over x, 1 over 1 minus x into x respectively. Get 3 equations consisting of this, so those we get a formula for x. Yep. That's the idea. Now hopefully this won't just completely eliminate the system and create a linear dependence. Yay! So if we take swap rows 1 and 2, make this one O2 2/3 and O2 1/3. Then we can go and say, let's move take this one and subtract row 2. So row 3 subtract row 2. 2, row 2. Jeez. So we're going to get 0 in the first term, 1 remains in the second, and a -4 in the third. Good. It's not linearly dependent. And then 2 of those is going to be -4/3. And -1/2 is going to be -8. And 3 more. It's going to be -11/6. Okay. Gonna take row 3 and subtract half of what is now row 2. It used to be row 1 at the top. So what? Gotta stop doing that. Really? You're not gonna? Okay. 2/3. 1/2. That's probably just a bad idea. Oh no. Our undo has apparently broken again. Cool, cool. 213. This is going to be O minus 1/2 of row 2 gets us a 0 here. Minus 1/2 of row 2 gets us -4.5, so -9/2. And this is going to be -11/6 minus 3/2. So that's going to be 9/6, which is -26, which is -10/3. Yeah, that's a familiar number. Okay. If we, no, seriously, multiply row 3 by -2/9. Lately it's been doing that, and I don't understand. Like, there's no real reason for it. 102 2/3. 0 2 1 3 0 0 1, and multiply by -2/9 gets us a positive 20/27. Okay, so if we take this, we're going to subtract row 3 from row 2 up here, and then afterward we'll multiply by 1/2, because I just like making things difficult for myself. This is going to be row 1 minus row 3 to row 3. Knock that bit off. Okay, so 1 0 0. 2 of row 3 knocks off the 2 there. 2 of row 3 is going to be 40/27. Off of 2/3 is going to be 18/27. So 18 minus 40 is going to be a -22/27. Hey, we got an answer. This is going to be 0 1 0. I know that much. Right, so row 2 minus row 3. 3 minus 20/27 is going to be, that's going to be 60, 70, 81. Oh, right, duh. Ugh. 81/27. 81 minus 20 is going to be 61, and 1/2 of that is going to be 61/54. Yay! And 001 20/27. Okay, now what was what? I mean, I could have stopped a long time ago here at some point. Third one. 20/27. This is equal to f of 3. Now, anybody who's watched the video will be able to tell me whether that's right or wrong. I actually only got to the point where I was like, well, let's try to figure this out. And then the guy from Another Roof had a couple of insights and ideas, and then I was like, all right, I'm stopping there because I don't want to I don't want to go too far into it and then get ruined. And it very well could be that there are multiple approaches to it. Okay, so let's look at calculus, because again, I tried to create a differential equation out of it, which was probably not the approach. But, so again, this was f of x plus 2f of 1 over 1 minus x is equal to x, where x equals 3. Or fine, whatever, that's fine. Alright, so here I was like, alright, let's try differentiating this. So take the differential of f of x, we just get f prime of x, plus 2 times. Here we get f prime of, by the chain rule, 1 over 1 minus x times. And now to take the derivative of 1 over 1 minus x, it's going to be a negative 1 over parentheses 1 minus x squared is equal to 1. Yeah, and at this point I was like, alright, now what? I tried to get rid of this so that I could just have the two portions that were going to be together, but then at the same time, if I try to take a derivative again, I do get a 0 there for a constant, but now we have a product rule, and so this expands out to 3 terms, or, well, that expands to 2 terms plus the one from before. So this isn't really getting anywhere. And if we want to find zeros or other critical points, like x equals 1, that's about it. It's about all we can figure from here anyway. So this kind of ran into a dead end, but that's fine. Oh, I said let's try to do like series solutions. So if we get it into a differential equation like I did here, then we could also say, okay, let's do let f of x equal power series. K goes from 1 to infinity of a sub k times x to the k. K minus 1? Yeah. Start from 0. It's fine. Alright, so then f prime would then be equal to, this would be the series as k goes from, from 1 to infinity of k times a sub k times x to the k minus 1. Whoa. Hector, thank you very much for the bits. Let me know if I can do anything for you in terms of, what in the bloody hell? In terms of answering in mathy type questions. My name is Obi-Wan Pez, this is N Simplex Pachinko. We strive to make everybody happy and create a, cozy mathematical community. So let us know if you have any questions. Oh god, it's just making it worse. No, like just stop. There you go. Now that it looks awful, we can agree that that was not supposed to be a 0 or an O. Okay. So reason that this one works is that we're taking we're taking the derivative of every individual term, which then goes from just a constant a sub 0 times x to the 0 plus a sub 1 times a to the first, x to the first. And when we take the derivative of those, right, the x to the 0, nope. Yeah, now that works. The x to the 0 term, we could say, oh, well, look at that. A, it's a constant, so we take its derivative and it's 0. Or B, we take the 0 down, knock it out front as part of the power rule. So 0 times x to the negative first. Either way, it's gone. So our k equals 0 term is going to be gone for our derivative. Still have hope that that's actually going to work, but it just isn't. Okay, so in this particular case, we'd end up with the sum as k goes from 1 to infinity of k, a sub k, times x to the k minus 1, plus 2. Nope, that was... No, that's okay. Never mind. Sum, k goes from 1 to infinity of, and this is where it becomes potentially a problem. Now the x is the thing that changes. It's not that bad. K times a sub k multiplied by 1 over 1 minus x raised to the k minus 1 times a negative 1 over 1 minus x parentheses squared is equal to 1. So yeah, this is getting possibly a little gross, but yeah. Right, these have equal indices, so at least they would be able to combine directly. Yeah, this may just be really gross. Okay, so all this stuff here, all of our individual terms are going to turn to zeros. Over here, there's only one term that's not going to be 0, and it's that one. So it looks like we're just going to get 1 equals 1. Oh, you know what? We can't even. No, we can't get that. Never mind. Because, right, we're never going to get a constant term. So it doesn't matter anyway. None of this works with this stuff. Yeah, we'll just leave it as monument to my failure. The other option was like Taylor series. Again, if we look at it in terms of the original, it's f of x plus 2f of 1 over 1 minus x equals x. And we're looking at this and saying, okay, what if we go with the power series that we had before, where all of these things are going to end up being k goes from 0 to infinity of a sub k x to the k plus 2 series k goes from 0 to infinity. Hey, Sensation Black. Yeah, no, I mean, that's true. Always fair. Right, a sub k times, in this case again, 1 over 1 minus x to the k. That's going to be equal to, no, just x. Damn. I did say way at the beginning before a lot of people got here that, like, a lot of times when they're looking for actual interview questions, if there's not an outright answer, or if you don't have, like, if you personally don't know what the answer is going to be, or don't have a route to get there, like I said, I never took number theory, so there's a lot of stuff I'm missing. Then at least they just want to hear, like, how you work through it, what your thought process is. If you know what the answer is just kind of like off the top of your head, that's boring. They don't want to do that. Older than the Incan Empire. Oh, man. Right, so I was coming up to this thing, and I was like, again, this is going to just create something gross. We're going to end up with, what is this, a sub 1 minus 1, because of the x on the other side. But, like, that's the only interesting thing that's going to change here. And again, the terms aren't going to add together nicely, so it's just going to be weird. So, I was hoping that, like, this would do something. Just because it is the yep. It is something that looks like a Taylor series itself, but it's on the inside, not on the outside, and it's just not panning out, so we're just gonna leave it. So we did actually figure out an answer to it, and that was if we figured out this nesting. So if I moved f of x to one side, and, sorry, you can't see that. If we move f of x to one side, and then we get f of 1 over 1 minus x and the x term to the other, then we can actually say, okay, what is f of 1 over 1 minus x going to be? So then we nested 1 over 1 minus x is going to be 1 over 1 minus x minus 2 times f of 1 over 1 minus 1 over 1 minus x. And then we could do this recursively as many times as we needed to figure out what this is going to be. Stokey, thank you so much for catching that one on me. Took a misstep quite a bit there, but hey, whatever. So we found out that this ends up with 3 cycle. So we can get f of negative a half, f of 2/3, and f of 3, and equations for all those things out of it. And then we can create a 3x3 system of equations, or simultaneous equations, as many of you know it, and set that up. Do the linear algebra necessary to figure out that f of 3 was going to be 20 over 27. Woo! Right. I didn't think there was any real being able to just plug in a bunch of numbers and see what happens. I wasn't really getting anywhere with that when I was just doing it off of my own. Oh, I did want to do one other thing, which was, you know, can we find a steady state where we'd end up with, you know, somewhere that x on the inside here and 1 over 1 minus x were going to be the same number, so that we'd be able to solve for that term and just say, oh look, they're the same now, and then move them together. So the answer here, short answer, no, you can't do that. But longer answer, why not? Right, so if we multiply both sides by 1 minus x, then over here we get negative x squared plus x, and over on the right we just get 1. Shift everything to the right, and we get 0 is equal to x squared minus x plus 1. And for this, we can immediately see that if we have to have the same signs, then we're not going to get at least rational solutions to make that happen. And then we can say, okay, well, how about real solutions? Anything at all? Is there some real gross, like, you know, irrational number or something like that? And then we say, okay, well, do the determinant. B squared minus 4ac. We get a negative 1 squared minus 4 times 1 times 1. So, no. 1 minus 4 is going to be negative 3. Since this is less than 0, we're going to get complex solutions. Complex, non-real. So there is no steady state for which we're just going to end up getting the same number in for our inputs of f. All right, and then I also tried to figure out, like, is there a way to get just the negative of the same thing so that we might be able to do something? I don't know. That came out, again, fruitless, not really surprising. It wasn't going to be anything there. And then I did another one where I did say, when I did try to get the negative of x is equal to our 1 over 1 minus x. So are we going to get the same value but different signs? Then this ends up being just x squared minus x equals 1. So x squared minus x minus 1 is equal to 0. Oh, gross. Why did I do that? I apparently got answers. That's why I didn't find that's why it didn't cooperate with me. I got like 2. I don't know how I managed to do that. Right, so b squared minus 4ac again, we get the same deal, but this time it's going to be 1 plus 4, so we get square root of 5. Plus or minus, this is going to be positive 1 all over 2. So here we end up getting phi, right, the golden ratio. Or at least the positive version of it. And then, oh, right, that should have been obvious. Can we get the number where just the number and the ratio are very similar to each other? And then I went back and plugged it in to figure out what we would get for each of those values. So that's what I actually did tonight. And I figured it out on stream. Woo! Because I hadn't done that in my page worth of notes here. So most of this is the BS that I just put on the screen, where I'm just like, I don't know what I'm doing, and flailing all around. It wasn't until I got here in front of you all that I somehow managed to remember there's a different way to do it. So 1,000 cranes, I came up with that a different way. I'd said originally that, oh, we're just gonna plug this in. We end up with f of x is equal to x minus 2 times f of 1 over 1 minus x. And then I said, what's this one going to be? So f of 1 over 1 minus x is going to be equal to, and that's what this is. Like I didn't even think to put the number in and just come up with it like that. I came up with the full nested fraction nonsense, and eventually got to that cycle. Yeah. So again, I saw this on the channel Another Roof from YouTube. And again, I was watching this video on the Oxford interview question. He's also got another one on his channel dealing with the movie X plus Y, which I thought was a pretty good movie. A little weird. He also enjoyed it somewhat. Yep, okay. And did you all get the same thing? 2027s, I think it was. Yeah. So f of 1 plus root 5 over 2 plus 2 times f of 1 over 1 minus, parentheses, 1 plus root 5 over 2 is equal to 1 plus root 5 over 2. So yeah, this is 1 over 1 minus a half is going to be positive a half minus our root 5 over 2. Just put it all over 2 like that. 2f of that's fine. This is fine. Right, 2 can go to the top. And then we multiply by the we multiply by the conjugate, which is 1 plus root 5. Top and bottom, we end up with 1 minus 5, just as is. So yeah, this is f of negative 4 on the bottom. 2 divided by negative 4 is going to be a negative 1/2, and then this is going to be negative 1 plus root 5 over 2. So yeah, the way I had been looking at it before. All right, and if anybody has any questions, feel free to drop them in chat. Otherwise, we'll continue on and look through some of the other random stuff I got going on. There was somebody in Penn's chat that I was asking, or that was asking questions, and I said, you know, feel free to stop by my place and like ask why something works, because I usually like to delve and go into all sorts of depths that a lot of other people may not like. Or at least, you know, I know the philosophy that Danny Highway puts out there is, look, I'm going to get you to figure out how the answer works, or like how to get the answer. Figuring out how all of the stuff works is not really my job. Which is perfectly fine for a math tutor. And especially for a busy stream, could also be an option. Okay, so the other thing that another roof was working on, in fact, I can go the other way. Again, this was one that I had seen. It was a it was a Halloween video from, I don't know if it was this year or last, but it is a circle that is encapsulated with, like, you know, cordoned off by a line that is horizontal and tangent to the bottom of the circle. And the curve itself is tangent at the top and falls off as we go further and further out to either side. It has a special definition, so naturally it's going to be like defined in a special way. Okay, so it was defined as every point on the curve is found by, man, I'm not going to get this right, am I? Every point on the curve yeah, I'm definitely not going to get it right. Alright, just going to have to look it up. Ah, okay. I'm missing a second line. Of course I am. Okay. So we got a second line on the top. If we draw a line that goes from the bottommost point through any point on the circle, then the point on the curve is going to share the same x value. That's what it was. Same x value as the tangent line point at the top. So then we draw this down, and it shares the same y value as the point from the circle. So actually it should be here. Something like that. It's not a tangent, sorry. So yeah, I liked this one. Just looking at it real quick and saying like, okay, how do we make this? How do we define this particular curve? How do we define all the little bits? So here, this particular xy value, again, gets the x value from the place where the line coming out of the bottom of the circle hits the line up at the top, and compared with the y value that it shares with the point that that line also connects with the circle. So if we wanted to draw another one, right, we can just pick any random point like way out here. Again, here, this is going to have same y value as this one. Totally has the same y value. I don't know what you're talking about. And shares the same x value as this point here. So that's where the actual curve should be. Etc. Anyway. So then the question comes like, how do you find any of these individual points along the actual curve itself? How can you define it? And so my initial thought was, okay, well, we're going to obviously define what this angle is in all of these individual cases, because we're starting from that bottommost point, which usually is at the origin. So 0, 0. And we're measuring that angle from the positive x-axis. So naturally, I'm a trig teacher, right? Everything is in terms of trigonometry. So in this case, it's a little more literal. Right, so if we look at all of our angles that we're going through as we move through this whole arc, starting from 0 degrees and then working all the way around to 180. Yes, starting from 0 going to pi radians. Then what are we going to get for the individual points that are in all of these locations? So we can extend this and say, okay, if we wanted the point that went all the way out here, normally we're doing this on a unit circle, radius 1, so we say it's going to have the same radius as the circle we had up above. And this is not just a simple shift. This is going to need to be done in parametric equations or polar. Because I haven't taught this in so long, right? R equals sine theta? I think it should be that one. Like these are our theta values that we get. Okay, if we just copy this circle, center it at 0, 0. This is gonna suck. You know what? Hang on. Take that. Add the other circle to it. Copy them. Move this whole complex thing down here. Now we can look at it from this perspective. Maybe this isn't helping, but okay, so from here we're looking at any particular location. Right, and we want it to get to there. So we need to look at like all three of these triangles. All right. Gonna step out for 1 minute. Be right back. We'll continue this. Like I said, 1 minute. Okay. So now that we've got this, our if we drop altitudes down, then this one right here is going to be the sine of theta, right? The unit circle that we actually care about. It's going to get us our vertical value equal to the sine of theta. And its radius is going to be 1. Okay, now for this inner one here, the radius is equal to the sine of theta, because that's what we figured out from up top. So if we multiply by the sine of theta to get the radius to get the other radius to become the new radius, then we have to multiply by the sine of theta to get the vertical to become the new vertical. So that means that this new vertical is going to be sine squared of theta. So provided I didn't mess anything up real bad, right? This location is going to have a y value equal to the sine squared of theta. Where theta is being measured in the usual way from the positive x-axis up to wherever we're ending our terminal side. Okay, and then the other question is, what are we getting for the x value? So we need to scale this up to the much bigger triangle out here. Right, where's this location? This is similar to our tangent secant stuff that we've been dealing with. Yup. Okay, so let's go like this. This distance here is going to be 2. It's an awesome 2. Right, this distance here has got to be 2 because it's 2 radii across. It's the diameter of one of our circles. So if this is 2, then now we've scaled sine of theta up to 2. So sine of theta over 2, it's got to be in proportion with, I guess, the 1 on the hypotenuse side up to whatever we want to call our diagonal. Capital R for the big radius. No, you know what? I don't want to do that one. I want to do the horizontal, because that's what we're looking for. We want to know what the x distance is going to be. Right? Yeah. We want to know what the x distance is going to be for that particular point. So we know that the little one in here is going to be the cosine of theta. So sine to 2 has to be cosine to capital X. Right, the big X value. So X is going to be, we're going to trade stuff around. Ugh. X is going to be equal to 2 cotangent of theta. I feel like he and I use different angles. That's probably why. Okay. So let's look into Desmos and see what we're going to get. So the weird thing about this is that because this is done, because we have theta, we need to do a parameterization. So we want the set of points that are, this was 2 cotangent theta, comma, sine squared theta. Cool. Okay. T then, because this might actually work. Yeah. Okay, and we go from negative infinity. Oh, come on. Negative 50 to 50. There you go. Right. So this one's called the curve is called the Witch of Agnesi, which he wanted to make a point that this was originally this was originally done by Maria Gaetana Agnesi, and she was one of the first women mathematicians to really get any sort of, she was the first woman to write a mathematics handbook and the first woman appointed as a mathematics professor at a university in Italy. That was in the 1700s. She lived to the age of 80 and was also the tutor to her 20 siblings, I think was the... Yep, one of 21 children. Pietro Agnesi, her father, was a wealthy silk merchant, and Maria Teresa Agnesi Pinottini was a harpsichordist and composer, was her sister. So if anybody's really big into music, might know her. But, yep, did a whole bunch of charitable work. Wrote the first book, credited with writing the first book discussing both differential and integral calculus. So, it's even predating, it's postdating the invention of differential and integral calculus, but it is yeah, cool. Damn it. But it is after why am I having this massive Leibniz? There we go. There you go. Yep, r equals sine of theta. Gets us a circle. And the Witch of Agnesi is this curve on top of it, which does some really cool stuff. And we haven't even touched, the half of it, which, again, you should watch the video on Another Roof, because he does an awesome job with it. And also all of the random disclaimers. Apparently, witch was a mistranslation from Italian. It was supposed to be like sailing sheet or something like that, and became witch. And then he makes a point to highlight the fact that like women have been underrepresented in mathematics and academics in general, especially in Europe, especially through Middle Ages and classical period and all that, or not classical. I mean, yes, classical, but throughout time up until the modern period. And the fact that witch might be associated with her is maybe a negative connotation that we don't want to get into. So, or rather, we want to talk about it so that it doesn't stick in the way that, you know, some bigot out there might want it to. Alright, so there were a couple of things that, like, this also starts doing something a little weird. No, I think it'll be fine. Okay. I need to realign and figure out like where exactly all of this is supposed to be, but it's fine. It's just my head that's messed up, so it's all good. Alright, so if we eliminate that one, just go back to the original. Yeah. Okay. See, this is the thing. He did it in terms of the central angle. And I was doing it in terms of the like standard position angle. So that's why this is all messed up. All right, we'll still do it in terms of the central or we'll still do it in terms of the standard position angle, which is going to mess everything up in terms of like I am not following his script. Which, you know, that's a good thing. Okay, so we got 2 cotangent theta down here. Again, this is a completely different angle than the one he was talking about. It also makes it a lot harder to like see what it is that I'm trying to do, but sure, it'll work. I think. I guess here's another way to think about it. Do you know the relationship between the sector areas of sectors that have the same endpoints on the chord, but then like put its other the vertex point elsewhere, like on the circle versus in the center? Is that one a nice one? I'm not sure area is. Like the angle is always half when it's on the outside of the circle compared to the center. That's easy. But I'm not sure area is. Let's see. So sector, area, circle from a point on the circle. I mean, I guess that... No, well... right? I mean, I guess we could just use the calc stuff, right? Because we've got calc stuff. Right? How do you do... Alright, Krayzik, don't fail me. Erwin Krayzik has a very nice applied mathematical book. I found some of the explanations to be helpful. Maybe it's not the best book or whatever, but I don't know, I liked it. It is a pretty good reference for applied engineering and, like, you know, mathematics for engineering. And it combines multivariate calculus, differential equations, and linear algebra into one combined book. So it made it very nice when I was trying to figure out like how to do stuff. So integrals of polar... I mean, I should just look it up online, really. Polar coordinates, form of complex numbers. Nope. Oh well. Oh, and at some point, I know Angela Collier, the one of the awesome physics people on YouTube, also said, like, you know, what are some good physics books that you might have gone into if you wanted to, like, you know, get into working out physics and stuff like that. And at some point she had mentioned the Feynman Lectures on Physics, and I found myself a copy of all three of them. Maybe it was a little expensive, I don't know. But volumes 1, 2, and 3, they are available for free online, digitally, if you want to actually just download them. I was thinking at some point I might want to actually go through and, like, have that. Kind of like how I know Penn and Zach have both done a couple of, like, different courses and stuff like that, where they've been like, hey, let's walk through this particular thing, because I don't know how to do it either. And I was thinking, like, it might be a good thing for me at some point to go through the Feynman Lectures on Physics and, like, work out the problems that are in there. Angela Collier said, like, it's at least halfway decent. It gets a little bit wobbly in Volume 3 when he started talking about modern physics, which is, you know, like quantum mechanics and things like that. Which, again, if you think you understand quantum mechanics, you don't understand quantum mechanics. So I don't know. I thought it might be an interesting endeavor to at least try. Let's see. Polar integral. Man, I'm just doing something easy. No, not complex analysis. Yeah, more like that. Okay. We don't need a double integral for that. We just want a single integral. It's like Calc 2 stuff, right? I don't need double integral. Yeah, area with polar coordinates. There we go. Okay, Paul's to the rescue. Um, if anybody hasn't been to Paul's online notes, it's absolutely wonderful. It's at the tutorial.math.lamar.edu. So Lamar University. There we go. Okay, so the area is going to be equal to alpha to beta of 1/2 r squared d theta. So r is going to be a function, but in this particular case, it's, again, r is equal to sine theta we had up here. So, yeah, not too bad. R is the function r of theta. Okay, there we go. That's behind me. I need to move. Okay, so here we say that we're going to take this and we're going to go with from. We wanted the... Yeah, let's try to find the area. So we want the area from theta 1 to theta 2. Of the circle, just sine theta d theta, and that's 1/2. So because that is that, it's going to be sine squared d theta. That's also then going to give us 1/2. Okay, for this we need to do a power reduction formula because we don't have a nice u and du to match up. So in this particular case, we've got to think about our trig stuff. So sine squared of theta comes from the cosine of 2 theta formula. So this is going to be 1 minus 2 sine squared theta as our trig. Come on. As our trig formula. Then we just need to solve for sine squared of theta. So I suggest usually moving this way and this way. So that gets us 2 sine squared theta is equal to 1 minus cosine of 2 theta. And then we divide by 2 for all of it. So sine squared theta is equal to 1 minus cosine 2 theta. If you ever don't know these, right, it's super easy to get lost in some of them. But really the only trig formula that you need to like absolutely know are going to be the sum and difference formulas. And then how to get the other ones. You can reduce your cognitive load by just remembering them, but it is a good idea to actually derive them for yourself to make sure that you understand like where they came about. And then as you use them more and more, it just becomes super easy. And like I said, I actually do this. I don't like memorize the square formula to power reduce. I know the double angle formulas. So my double angle formula that I just absolutely know off the top of my head is going to be cosine squared theta minus sine squared theta. And then when I remember this, I also remember the lower one. And the other one where we have 2 cosine squared theta minus 1. So I just remember it that way in particular. Whatever works for you, really. So if we do theta 1 to theta 2... Alright, then this is going to be, again, 1/2 minus 1/2 cosine 2 theta d theta. Okay. This is going to be a 1/4 theta minus 1/4. Integral of a cosine is going to be a sine of 2 theta, but we needed an extra 2 in order to have d theta in, 2 d theta is the derivative of 2 theta on the inside of this, so that gets us an extra half stuck on the outside. So that's going to be an overall 1/8, and then that's going to be evaluated from theta 1 to theta 2. That's equal to 1/4 theta minus 1/8 sine of 2 theta. Again, theta 1 to theta 2. Alright, so the area for this thing is going to be equal to 1/4 theta 2 minus theta 1. And minus 1/8 sine of 2 theta 2 plus 1/8 sine of 2 theta 1. Okay, so this is the area of the sector. Now, I don't know that this is going to work as nicely as I want it to, but what is the area of the wedge between this x value here and this x value here? So that is going to be Yep, it's going to work. Yeah. It's going to be the integral of the function sine squared of theta d theta between here. This is going to be the x value on top there, 2 cotangent. Ew. Theta 1 and 2
Raiding party!
Theta 2. It's a raiding party. Hello, everybody. I didn't actually hear it. That's kind of sad. Oh. Thank you, everybody. Hey. Welcome, Zach, Penn, Don. How we doing? Hope your mathing was very nice tonight. What'd you all end up doing? Yep, nice. Gonna need to work on the notes from that. Hey, Danny. Yeah, I know, right? I'm gonna have to go back and watch some of the stuff from there too. So, we've been working on the problems from Another Roof on YouTube that I saw today. So, one of them was the Oxford interview question. What is, oops, if we have f of x plus 2 times f of 1 over 1 minus x is equal to x, what is the value of f of 3? So I did a page of all sorts of notes and stuff like that, and we talked here about like what are different ways to potentially solve this using like all this other weird stuff. And then I like wrote out all of them, and then the first one that I picked to do tonight, which was a new inroad that I hadn't actually tried on my paper, worked. So yay. Had nothing to do with any of the stuff I'd done all day. It's cool. And then the second one was looking at the Witch of Agnesi, which is this curve here, which is defined as being the curve that is based on this particular circle. If we draw a... So it can go either way. We can go from the center point out to these individual locations, or we can go from the bottom where we have the standard position 0, 0 as the vertex of our angle. I chose to go with that one. Maybe that was a terrible idea. We're trying to do some math to figure out if it's identical, which, I mean, of course it is, but, you know. How is doing stuff from the center point going to be slightly different from doing stuff from an outer point? So it's been interesting. Let's see. So where we are currently, that's okay, ZF. So we got what we're doing at the moment is we said that the curve itself is defined by taking a point from the bottom of the circle and drawing it out to a line which is parallel to our x-axis, which in this particular case is going to just be y equals 1. Now it could be any number you want, right? It's just y equals a, some sort of constant. But I said let's just have it be y equals 1 to make it easy this time around. Right, so y equals 0 is our x-axis underneath it. Y equals 1 is going to bound it on top. And we said if we draw a line that goes from the bottom all the way up to... You can't see that. Keep doing this. Limit approaches to infinity and simple integrals. Yeah. No, we're good. This is just trig. So I am a trig teacher, and so this caught my eye as soon as I saw it. I was like, yes, we're gonna look at this. So going from 0, 0, drawing our line out to the top here through this particular angle, theta 2, is going to get us this triangle here, and then this little triangle here. The curve is going to be defined by the x value that this line connects with the y equals 1 top line, and the y value that it connects with the circle r equals sine of theta. So if you know your boo pre-roll. All right, anyway. We'll hang on for a few minutes at least. So anyway, yeah, the y value is shared by this location on the circle that our line went through. So if we do that for all possible values on the circle, all possible locations on the circle, so theta 1 down here, we go through there, that's our y value. And then here, keep going, keep going, keep going, keep going, bam, that's our x value. The name of it, The Witch, actually comes from a mistranslation of a sailing sheet. And okay, stop hitting things. And Agnesi is the woman Maria. Oh, come on. I should have remembered this. Maria Gaetana Agnesi. Who was a woman mathematician in the 1700s who originally was tutor to her 20 siblings. Yes, 20. And also the first woman to ever print a mathematics handbook, and the first woman to ever print a treatise on differential and integral calculus together. In fact, she may have been the first person first mathematician to print one together, which was a little bit weird to me. I would have thought that Leibniz would do it, but apparently not. Because we all know Newton didn't do it. Shots fired. Okay, so we said, how are we going to get the locations of these things? All of our XY coordinates are kind of hard to specifically find. So I said, okay, let's work it out like this. We're going to do our unit circle here, and then the circle r equals sine of theta up here. That, you still can't see that. Unit circle here, and r equals sine of theta up here. So I drew out just a line and said, let's measure all of our points from here. Our unit circle gets this point out here. It drops down. This is going to get our sine of theta going vertically and our cosine of theta going horizontally out to this point. And then from here, and this is the whole reason we use the unit circle, now we can scale this down to the smaller triangle we create for the first intersection point with the other circle. And then the larger triangle we can scale up to get this one, which is going to be based on the intersection point with y equals 1. So when we do that, we find that the smaller triangle has y value, sine squared of theta, and horizontal value was, what was it? I mean, we don't care because it's not technically a part of our answer, but you know. How do we do that? We scaled cosine down by a factor of multiply by sine. So the third side, the horizontal side of our small triangle is sine theta cosine theta. Hey Zach, question. Are you planning on doing 2 sections of real analysis per Tuesday, Thursday? Sorry if you left. All right. So now my purpose is to verify. Yeah, okay. My purpose that I'm doing now is to verify that, that the I didn't know if it was one session in the morning, one session in the afternoon, and trying to repeat so that everybody has a chance to get it. But yeah, it's on video on demand, so what does it matter, right? Verify that the area that we receive from the sector based on the sector that we found here. All right, but it's not a sector technically because it's not from the central angle. ... So this like pseudo sector that's going from here to here. Find that area and then look at the relationship that exists under the curve for this thing here, which is parameterized as 2 cotangent theta sine squared theta. So, but that's not d theta, is it? It's dx. Right. This is not d theta, it's dx. How does that work? The y values are sine squared of theta. But it's not theta. No, it is theta. Okay, because it's based on the original theta. But then it's dx over here. Okay. Right, x equals. So then how do we resolve this? So we got to know what dx is in terms of theta. Our x is equal to cotangent theta, I guess. So dx not cosine, cotangent. So dx is going to be -2 secant squared theta d theta. Okay, so in order to not mix variables, because you all know how I feel about that, this is then going to be multiplied by -2 secant squared theta d theta, which is cosine squared at the bottom, which makes this -2 integral to cotangent theta 2 to cotangent theta 1. And this is now a tangent squared theta d theta. Boo. Integral of tangent squared is just going to be, oops, nope. Nope, that's not secant squared that we take the derivative of to get tangent. Right, so that also requires power reduction. Hooray! Okay, now the good news is that the power reduction for tangent is actually fairly simple. It's just the power reduction of the sine divided by cosine. So sine squared theta over cosine squared theta is equal to this was going to be 1 minus cosine of 2 theta, and this is 1 plus cosine of 2 theta. They're all over 2, so that just divides out. That's fine. That doesn't make it any nicer, I don't think, but sort of makes it nicer. If we multiply both top and bottom by 1 minus cosine of 2 theta, does it make it any nicer? Maybe. This is going to be 1 minus 2 cosine 2 theta plus cosine squared 2 theta, which we can deal with, over 1 minus cosine squared 2 theta, which is just going to be sine squared. are we back in more or less the same position we started in? You get some extra stuff, but now we got cotangent squared. Yeah, okay. Alright, I think I will just go ahead and ask it what it thinks it's doing. Tangent squared of x. Okay. Okay, can tangent square be done by integration by parts? Ew. Doesn't really look like it. Oh. Secant. Secant squared theta minus 1. Oh, man. It's just awful. Alright. So -2 integral secant squared theta minus 1 d theta. God. 2 cotangent theta 2 to 2 cotangent theta 1. Okay. -2 times the quantity of the tangent of theta minus theta. Evaluated from 2 cotangent theta 2 to cotangent theta 1. Next question. Is that supposed to be inverse or something? No, it would be cotangent of theta. So that's not an issue. Okay. Right, because x moves up there, sine moves over, 2 moves over. Yeah. cosine to x as sine is to 2. Yep. Now we've got a tangent, or yeah, tangent of a cotangent. That's aggravating. Oh, that's where it's not, because those are x values. Again, we need the theta values. Right, these are x values. So we need to solve for theta. Okay. So theta 2 is equal to inverse cotangent of x over 2, which is the inverse tangent of 2 over x. And same with up top. Right, this is going to be x. Ooh. Which ones were they? Theta 1 was the further one out. So that's where we ended. So yeah, that's x2, x1. If we define them that way. x1, x2. Similarly, theta 1 is going to be equal to the inverse tangent of 2 over x2. Yep. So this is going to be negative 2 times the tangent of the inverse tangent of 2 over x2 minus theta 1, its angular value. Okay, and then this is going to be a plus 2 tangent of the inverse tangent of 2 over x1 minus theta 2. Okay. So this is going to be the area under the curve, the wedge. So this is going to be 2 times the quantity. Right, this is going to be the negative tangent of the inverse tangent of 2 over x2. It's in either quadrant 1 or 2. So, if it's in quadrant 2, technically we end up with the other answer, but then we can work it back around the other way. Anyway, doesn't matter. Now, we still get the same tangent value. It doesn't matter. We're good. So the tangent of the inverse tangent is just going to get us 2 over x2, yeah? Right, 2, the full distance here over the full distance horizontally. Yeah. Well, let's just make sure. Tangent of 2 over x2 opposite over adjacent is going to be angle theta 1, which when we take the tangent of theta 1, we can then get any of these that we want. So it doesn't have to be necessarily 2 over theta or 2 over x2. But that's the nicest one. It's in terms of all those things. Rather than, oh, you know what though? We can get it in terms of this stuff. Have our signs. And then we get our theta 1, theta 2 here, which are the ones that are exposed outside. Okay. This is going to be weird. So it could just be the tangent of theta 2, tangent of theta 1 can either be, yeah, it's just going to be sine theta over cosine theta, so it's just going to be tangent of theta. Yeah, it's just going to be tangent of theta. Yeah, I don't think we're going to get what we wanted here. Theta 1 minus theta 2 plus tangent theta 2. Yeah, we're not getting the same thing, but I could chalk it up to not actually taking the integrals from the same point. Because again, our sector area from the other circle is going to be from the central point rather than from the bottommost point. So if we were to take this from here, right, what's this sector area? So that's 1/2 r squared. Times your theta, I think, or times the alpha, I think, right? 5,000 other answers that wanted to tell me the other thing. Oh, yeah, so, 1/2. 1/2 r squared theta in radians. Yeah. So alpha in radians. That's perfectly fine. It's going to be our 1/2. And r is just 1. And the radians is going to be our theta 2. No, it's not going to be theta 2. Man. Wait. The angle's half as much from the outside as it is. Yeah, as it is from the central angle. Okay. So this is going to be alpha. Then alpha is twice theta 2 minus theta 1. Yeah. So it's just theta 2 minus theta 1 to get the area of that particular sector. Okay. Gross. Doing it this other way did not come up with the same thing, so what am I doing wrong? Anybody want to jump in, feel free. Alright, so our x values are all defined by 2 cotangent theta. Our y values are all defined by sine squared of theta. Alright. Next question. Is there anything to the fact that our d theta, going like this, is going to project dx out here? So can we directly relate those instead? Is it just -2 secant squared theta d theta? Or is there something else that's going to affect it? So dx is going to be the difference between the locations of, right, x2 minus x1, which is going to be approximately the locations of 2 cotangent. God damn it. Aye. Jerks. You know what? It's midnight, so that's probably a server reset. So dx is the difference between these two things. So I need to find a way to combine them into two functions. cosine sine minus sine cosine, right? It's going to be cosine of 2 theta. No. Cosine of theta 1. We have unlike functions. It's a sine. That we should solve? Yeah. Salji Babas. Thank you very much for the subscription to Prime. That is awesome. Or with Prime. I'll figure it out someday. Okay, so this is going to be theta 1 minus theta 2. Or perhaps theta 2 minus theta 1 would be easier. Doesn't really matter. Okay, divided by. This is just sine theta 1, sine theta 2. And for anybody who is a sub, feel free to use those emotes anywhere you want. I know the Yikes one is especially popular. Oh, really? Well, I can only actually grab the other one at the moment. Come on now. Oh. That's too bad. There you go, pop out. Alright, there we go. So the Yikes one is probably my favorite just because I'm not really good in the area of art. And so, but of course the only reason for that is I just don't practice. So, it was Science Streams. If we went over to talk with Balint, and he's a paleontologist from, or no, ant biologist from New Jersey, and he does some really cool stuff over there. He has also a Wacom Wednesday, and so Wacom Wednesday, go in, do your art stuff. So ended up going over there and having a good time, and just started doing some art. Eventually, imagine that, I got better at it. It's still not good, but you know, it's certainly better than it used to be. And I made a couple of emotes out of it, so. I do have a little bit of spare time this month, so we're going to try to do a couple more, or get a few different things going on there. I've been working on something for Raid Call that is a reference to, a blatant reference to Coheed and Cambria. Anybody who's fans, you'll recognize it when you see it. Oh, I think we might have it. -2 sine of this right here. Theta 1 minus theta 2 is d theta. And for small values of theta, for small values of x, sine of x is approximately the same. So dx, or d theta, is infinitesimally small. So that is just approximately d theta. Okay, I don't know if that actually is going to work for anything. And if theta 1 and theta 2 are approaching each other, then that's going to be sine squared at the denominator. So, hand wavy, dx should be approximately -2 over sine squared theta d theta. Oh. Oh, no, no, no. Wait. We said cosine. We said cosine. Huh. Oh, cosecant. Yep. No wonder. Alright, that messed it all up. Ugh. I was wondering what went wrong. Somebody should have stopped me. Okay, this is not tangent squared then. This is just going to be -2 d theta. Integral -2 d theta. That's it. -2 theta, evaluated from x1 to x2, which again are going to be our inverse tangent of, not even. Those are our x values. So theta 2 to theta 1 is going to be +2 theta 2 to theta 1, or theta 2 minus theta 1, that way. Okay, well it's not bad then. So that's off by a factor of 2. So the area of the witch is going to be twice as much as the area of the circle that we get, or the sector that we get. So if we want the entire thing, right, then this is going to end up being if this is radius 1, then area of the circle is going to be pi r squared is just pi. And the area of the witch is then going to be twice that. That feels like that was not the answer that he got. But right now, I think we're probably running out of time here. for me to stay sane. I mean, too late, but you know. Woo. Alright, so... Okay. I wonder how many copyright claims I'm going to get on this. Oh my goodness. My last several math videos have been hit with multiple copyright mutes because of the music I play in the background. It's like, you all can probably barely hear this anyway. But yeah, it's been slamming me up against the wall here and be like, mute 3 minutes, mute 3 minutes, mute 3 minutes on any one day. And Pretzel, the company that I use, is just like, just dispute it, it's fine. Like, make sure it's the right song, and then dispute it as you have the rights to do this because, you know, we did all the legwork for this. And then for the ones that don't, or any of them that are just wrong, you can highlight it and be like, nah, that's wrong. So the good news is that I just effed up over here, and the derivative of cotangent is negative cosecant squared. And like all of that tangent stuff just didn't matter. And then I re-verified how to get d theta from dx. I went through this and got all the way down to sine squared theta, and I went, yeah, sine squared theta. It's secant squared. And I just kind of went into a little. I had a moment there. That's when I realized, oh, yeah, that's the wrong integral or wrong derivative. So, C calculus students, we do it too. But I mean, it cleaned it up very nicely. So the actual integral that we get is only 2 theta 2 minus theta 1. and the area of the circle, the whole circle, is going to be pi times r squared, which is just 1, so pi. And then the area of the whole witch altogether, based on that, is going to be 0 to pi. So from 0 to pi, we're going to get 2 times pi. I do have a small potential problem in that I believe the sector from the central angle perspective is supposed to be a factor of 4 different from the area under the witch. So in which case I'm getting this slightly wrong, unless, yeah, I don't know. I'm not too worried about it. It's in the video. I probably messed something up. So go watch another Roofs video and you can see what that is. I am going to myself, before we go, do a quick redeem for points, because this is a new point redeem. John Gould's Guide to Main Lingo. So we're going to flip to a random page here, somewhere in the middle-ish. Okay. Okay. I'm gonna do... Yeah. Okay. Potted her fasts. P-A-R-T-E-D H-E-R F-A-S-T-S. Potted her fasts. A vessel gone astray from wharf or mooring has parted her fasts. Fasts being the lines that secure her. Accordingly, an overloaded clothesline that snaps off has parted her fasts. The term suits any similar situation. Lem Spofford had a pair of pants that gave him zipper trouble, and he said she potted her fast by herself. So, yeah, I made that only a 500 because I did put a cooldown on it, but I do want to get into that a bunch. I think that this is going to be like my thing. You know, the gimmick that's going to get people to be interested in my stream. So, like I said, I'm going to try to work on the mods for Baldur's Gate 3 so that I can actually get my Firbolg character in there. If not, I can probably manipulate it to be something else and just be one of the standard ones. You know. On Hero Forge, they don't have Firbolgs either. I ended up making him a bugbear, I think, and then just altering it slightly. Oh, yeah, actually, I can show that. Let me... Here he is. Yeah, so this is Fuzzy White Mountain. Storyteller Bard. Firbolg. So again, like I said, I made him like a bugbear, but you'd never notice all the fur, I guess, because it's all under. I mean, the coloration is ridiculous. Like, I'm going over the top on it because, of course, bards always go over the top. But, you know, give him the great. I kind of wanted it to be like this or something, but I couldn't quite get the open book. The only open books that they have are like spell books, which have like really weird eldritch stuff all over them, and I was like, I don't really want that. So I just put it like he has a journal in his hand, which is the, you know, his his particular thing. And yeah, so this is fun. I'm gonna see if, oh yeah, he's got plenty of time. I'm gonna send him to my friend who has a 3D printer, and we'll have him for at least a few months before I get going, and then I'll lock him away in something, go overseas and break him out during. Oh, I'm gonna break him out as a character for one of my future sessions. I just know it. The people in England are gonna be like, "What the? What is this?" All right. I think we're gonna probably call it here and see if we can't find somebody else doing something academically oriented. BB Dab, good evening. Thank you for following. Just totally missed your alert here, so sorry about that. But all right, we got Balint, who is on with Lita tonight, his spouse. They're doing some stuff with, looks like Lego build. Jesse Cox is doing the Invincible. Love that one. And nobody else is really doing anything else. I mean, we got a few people, but you know. Alright, so I'm going to send us over to Balint and Lita with Science Streams, and then I think I'm also going to pop open a window for Jesse Cox, because I want to see how he's doing on the Invincible. But thank you everybody for stopping in. I'm going to be back on Friday, certainly, for Baldur's Gate, and then we'll probably do some other random stuff. I don't know, we may have some time between now and then. Maybe some morning math. We'll see how everybody else is doing. I don't want to, you know, steal viewers away from anybody else, but alright. See y'all later. This is Obi-Wan Pez for N Simplex Pachinko. Have a good night.